Welcome to the Explainer. Let's just dive right in. Today, we're focusing on a foundational skill in Grade 8 Algebra I, which is translating messy, real-world situations, like figuring out exactly how much you're actually spending on takeout when all those ridiculous hidden fees pile up, into clean, powerful algebraic equations. You know, we interact with quantities all the time in our daily lives, but turning those interactions into formal mathematical claims takes a very specific set of steps.
Here's our roadmap for today. We'll set our learning target, model a real-world situation, translate that into words, tables, and symbols, look at equations as relationship claims, check our model, and finally wrap up with a recap and a transfer question.
Section 1. Setting the learning target. Let's take a quick look at exactly what we're setting out to achieve here.
By the end of this explainer, you're going to know exactly how to identify your known and unknown quantities, define your variables with really precise units, translate a verbal relationship into a math equation, and, most importantly, explain what that equation actually means in context. We don't just want to compute numbers, right? We want to truly understand what those numbers represent in the real world. Section 2. Modeling a real-world situation. So let's start with a scenario that, well, we honestly all know way too well. Ordering food and dealing with those sneaky delivery fees. Imagine you're ordering from your favorite local pizzeria. They charge a $5 fixed delivery fee no matter what, plus $12 per pizza. To model this mathematically, we've got to separate the info into two buckets. First, what do we actually know? Well, we know the $5 fixed fee and the $12 cost per pizza. But what's the unknown? That's the number of pizzas we're going to order, and ultimately, the total cost of the whole thing.
Now listen up, because this next step is absolutely crucial. It's where so many people get lost. We have to clearly define our variables and anchor them to specific real-world units. So let's say P equals the number of pizzas ordered, and we explicitly note the unit is literally pizzas. Then let C equal the total cost, and the unit there is dollars. Seriously, if we don't attach units, our numbers just kind of float away and lose their meaning entirely.
Moving on to Section 3. Words, tables, and symbols. Now that we have our variables set up with their precise units, let's translate this relationship using a few different methods just to see how the logic builds on itself.
A small table is actually a brilliant way to illustrate this pattern. Think about it. If we buy just one pizza, we multiply that $12 rate by 1, add our $5 delivery fee, and boom, total cost is $17. 2 pizzas? That's 12 times 2 plus 5, which equals $29. You can really start to see the regularity here, right? So if we jump down to our variable p, the math applied becomes 12 times p plus 5, which perfectly gives us our total cost variable, c. And just like that, our everyday scenario and that simple table give us a totally precise symbolic equation. C equals 12p plus 5. We've literally translated the real world straight into algebra. Section 4. Equations as relationship claims. Now, I want to pause for a second and zoom out, because we need to break a very, very common misconception about what we just did. Here's the deal. An equation isn't just some mysterious puzzle waiting to be solved. It's actually a definitive claim about how two things in the real world interact with each other. In Grade 8 algebra, we use these equations to describe situations where one quantity directly determines another. The equation we just wrote? It's simply making the claim that the total cost is fundamentally dependent on the number of pizzas ordered, and that it grows at a constant rate. This actually ties directly back to our core mathematical practices, the ability to reason abstractly and quantitatively. Basically, this means we need the ability to decontextualize, to pull a situation out of the messy real world and represent it cleanly with symbols like C and P. But then we have to be able to contextualize it right back, pausing to remember that those symbols are actually representing real-world dollars and physical pizzas. Section 5. Checking the model. Now, a model is really only as good as its proof, right? So let's run through 2 quick checks to make sure our algebraic claims actually hold up.
For our first check, let's look at a totally new stated relationship and figure out which equation perfectly matches it. Imagine you jump into a taxi. There's a $10 fixed fee just for getting in, and then a $3 charge per mile driven. So, which equation makes the correct claim here? Is it A, y equals 10x plus 3, or is it B, y equals 3x plus 10?
If you guessed B, you hit the nail on the head. And here's the reasoning. In this context, our variable x represents the miles driven, so the unit is miles. Our variable y represents the total cost in dollars. The rate of change, that $3 per mile, has to be the number that multiplies our variable x. The $10 fixed fee just stands completely alone because it doesn't change no matter how far we drive. Option A totally mixed up the fixed constant and the rate of change. Okay, for our second check, let's go back to our original pizza model and use substitution to verify our relationship. Step 1, we just substitute a sample value from our earlier table, let's say p equals 2 pizzas. Step 2, we run the calculation on our algebraic model. So 12 times 2 is 24 plus 5 equals 29. Step 3, we contextualize and verify that claim. Does ordering 2 pizzas actually cost $29? Yes, it absolutely does. If we had mixed up the units or if the math didn't match up here, we'd immediately know our algebraic claim was totally false.
Section 6, Recap and Transfer Question. You guys have done some fantastic work today following this process, so let's quickly recap everything we've learned, and then I'm going to leave you with a bit of a challenge.
Here's your quick 3-sentence recap to really lock this in. First, always identify your known quantities and define your variables with highly specific real-world units. Second, use tools like small tables to help you translate those verbal relationships into symbolic linear equations. And third, never forget that an equation is simply a mathematical claim about how quantities relate to one another in the real world. All right, now it's time to test yourself on modeling a brand new real-world relationship. Imagine you're buying concert tickets online. They cost $45 each, plus a wildly frustrating one-time $15 processing fee applied to the whole order. So what is the symbolic equation for the total cost? What are the specific units for your variables? And ultimately, what mathematical claim are you really making about this transaction? Take a moment to write it out, check your model, and see how algebra helps you perfectly define what's going on. Because once you realize that math isn't just about finding x, but is actually a tool for decoding the hidden rules of the world around you, well, you're going to start seeing these equations absolutely everywhere. Until next time, keep questioning the quantities.